session by sharing your PPT, sir.
Okay, madam.
Okay.
Can you see my screen?
Yes, sir.
Yes, sir.
Can you just tell me whether these slides are changing or not?
Yes, sir. It's changing.
Okay. Shall I start?
Yes, sir. Yes, sir.
Okay, so very good afternoon to everyone. So first of all, I'd like to thank Dr. Somesh for inviting me in this TTP program on AI and ML. So the topic that Sarah has already chosen for me, so my work was reduced. So the topic is based on the supervised learning theory and its application. So mostly there are a lot of supervised learning techniques are available that all of you know in the recent days. So I'll take off only one technique that is very important and very classical technique, that is called the base decision rule. So what is the mathematical theory uh, about this base decision rule and how the people can implement? So I'll give it to you, or I'll show you the implementation perspective on the satellite images. Okay, so to start with, so I'll have to discuss a little bit of basics of machine learning that all of you know. So nowadays people are taking a lot of attentions in this topic and trying to apply in different disciplines, not only computer science, in from across, other disciplines also. So mostly it can be classified in two parts that the people are working. One is called supervised classifications and another is called the clustering. Okay, or it is sometimes it is in the early days it used to call as a unsupervised classification. So now another important things whenever you are going to handle or deal with some data and you are applying some supervised classification technique, and we need to analyze this data before classifications. Okay, we need to analyze this data. So there are different space that you can handle or you can deal with for handling this data. One is called the measurement space, another is called the feature space, and next one is called the decision space. So now in the measurement space, as you can see, so sometimes this measurement space and feature space are used interchangeably. And this is called the decision space. So now how these things can be understood? Suppose you would like to classify the class of people into two categories. Suppose I am taking one category is called the Indian community, another category that I am taking for the Japanese community. Okay. Now, so you have to measure some attributes, or you need to measure, some features. And after doing the measurement of the features, so suppose I would like to measure the features like, let's say you can take the height of a person, like you can say weight of a person, and then you can say there's a different eye color, shape of the nose, or this that you can take this a hair color also. I mean a different type of features that you can take, and then you could transform this measurement space from the feature space that you can convert. Okay, so in this feature space, what you would like to do? So you will have to project these features in some two-dimensional space to see that whether the features are linearly separable or it is a non-linearly separable by seeing this scatter plot that you usually used to do. Then you will have to take a decision. Okay, so now in the decision space, because you need to have some decision boundary which distinguish between these two classes. So let's say for this example, we have Indian community and this one is Japanese community. But on the other way, in order to clearly understood this measurement space, suppose I would like to do the classifications between these, character recognitions problem. Suppose all of you know the term problem is called the character recognition problem. So now I have a character, let's say that is A, or an A can be written in the different trajectory that you can maintain. So now in the measurement space, to be understood more clearly, you need to digitize this character And firstly, you need to digitize this, then you will have to binarize it. So now the digitizations and transform it into binary image that can be done in the measurement space. Then after that, you have to extract some intrinsic attributes or intrinsic features from these images. Suppose you could take some geometrical features from the images, binary images. You could take some statistical features, or you could take some other also features. So to construct the feature vector. Then after that, you could take a decision. So now whenever you are going to have a decision, so now you will have to have some decision boundary, or you have to write some decision rule. So on what is the decision rule which distinguishes between these two classes? So that's why the three important things are very much to be understood. That is called the measurement space, feature space, and decision space. Now the main task of the your classifications, whenever you are doing this is a machine learning related things, then there is a two important tasks. I mean, it can be bifurcated into two ways. One is called the feature selection. So this is a huge amount of research are currently going on in the feature selection. Means these feature selections means you'll have to have take the subset of the features. Okay, from you have a, so how you are going to propose a new algorithm so that you can derive a subset of the features. Okay, you have a superset. From the superset, you will have to extract the subset of the features. So there are a lot of feature selections algorithm are available that I can just give it to the subnames, like this sequential forward selection algorithm, sequential backward selections, LR algorithm, branch and bound method. These are the standard feature selections algorithm. So to understand the feature selection algorithm, you need to know some criterion functions. So on what basis, whenever you are going to extract some features or you extract some subset of features, you need to satisfy some criterion function. Okay, so this is one area of research that people are working. So this is called the feature selection. Another way is called supervised and unsupervised classifications. Okay. So now, as my topic for this today's lecture is called the supervised classification, so I'm not talking about the supervised classification. So supervised classifications means you know the class level of these data points. Okay, I mean you know this. I mean this. What is this class level of our training data points that you know it. So now in supervised classifications, when you are going to do, these are two important cases that you may come across. So case number one, when you are going to apply some probabilistic measures or probabilistic based classification technique, then two things will be given to you. As for this lecture, I'll be talking about this one of the most important rule. This is called decision rule. It's called the Bayes decision rule. So to apply the Bayes decisions rule on your data set, then there are two things must be known beforehand. One is called the density function, or it is known as class conditional probability density functions. Okay, and next one is called the prior probability. So if two things has to be known to you, then only you can apply the Bayes decision. Another thing, points are given. It means that you know what is the class level of the data set. Okay, you know what is the class level of the sample points. So now, in a nutshell, to understand the machine learning, so you need to have a prerequisite knowledge about this linear algebra. You need to know a little bit of concept of the linear algebra, probability and statistics. Next is called the calculus. So three important concepts that you need to know. Otherwise, it will be a little bit difficult to understand because you need to handle a lot of mathematics. Okay, and for these things here, for this lecture, I'll be only talking about the Bayes decisions rule, and to understand the Bayes decision rule, that is, two things must be known to you. So now, in the real life data sets, as you can see that when you are going to be handling some real life data sets, so it is not possible all the time that prior probabilities will be given to you or the density functions will be given to you. Now, if the two things are not given to you, but still you can estimate the density function. So there are a lot of techniques for estimating the probability density function. Okay, one of the techniques that I would say this is called the maximum likelihood estimation, MLE. So this is very popular method that people are using. So if the density function is not given to you, but you could still estimate the density function from your training data points. Okay. Next is called the prior probabilities. So now, what is the meaning of the prior probabilities? So now these prior probabilities, it means that as I was taking an example of these things, like this Indian community and this Japanese community. Suppose that I have some populations. I have drawn some populations from one distribution, and this population from one this Japanese community, and this called the Indian community. So this is my capital M. Now the total number of points, sample points, are capital M. Now what I will do, I'll just mix them up. So I'll just mix them, the Japanese community and this Indian community together. Then what I will do, I'll draw, I mean, randomly this in one sample from the entire population, from the mixture of the population. So now when I am going to mix up, so now this population is called the mixture population. So from the mixture, you can draw some percentage. Suppose if I take 60% of my 60% that I will take from the mixture, that will be considered for the Indian community, and rest of 40% that I will take for this is in Japanese. Okay, then my prior probability for the class 1, so that is Japanese people, will be 0.6, and for the prior probability for the class 2, that is a 0.4. So you can just think of it in this. But when you just sum them up, when you just sum up the prior probability, so it should be 1. So the range of the prior probability is 0 to 1. It should not greater than 1. So please remember. So now at any point of time, if the prior probability is not given to you, so there is a way to estimate the prior probability. So that is formula is n1 by n and n2 by n. Now if you just sum them up, n1 plus n2 by n. So obviously this is 1. So in this way that you can do it. Okay, or I should write it so that it will be more easy to you understand. Suppose I would write, suppose if your total population is n. Okay, now this prior probability, that is P1, capital P1, whenever I'll be using capital P, it means it is a prior probability. Okay, and when I'll be using the small p, it is a density function. Now capital P1 will be, I should share, this is a n1 by n. So this is for the class 1, for C1, and for if you have this capital P2, that is called the prior probability for class C2, then I should write this is a n2 by n. So this is for, you can say, C2. So these are the way when the prior probabilities are not given to you. So then you can just mix them up, okay, and you draw randomly. So if you have, this is a, you can say this is a n1, it should be a 60%, that you could choose 60% of the entire population from the mixture population, and for n2 you can take, so that is a 40%. So in this way you can choose it. Okay, so now this, if prior probabilities are not given to you, you can estimate, and if the density function is not given to you, then also you can estimate this density. Now how you can estimate? So there is a technique is called MLE. So that is called the maximum likelihood estimate, MLE method. Okay, so now I don't have time to discuss all these things, but you can check. So why it is called? So do you know when a function is called a density function? So all the function you cannot say it is a density function. So a function is called a density function if it satisfies some property. Okay, so okay, I'll just tell you. So before this, what are the applications area of this AI and ML techniques that you can apply? So there's a machine vision you can apply. There's a character recognition that I was just explaining to you. This is OCR. This is a computer-aided diagnosis, means there is an early diagnosis of the different type of diseases, like it can be musculoskeletal disease, neurological disease. Then there's a people are working in the field of natural language processing. This is a very vital area. Nowadays, there's a different type of translator are developing by using, or you can say, automatic translation system by using these techniques. Then there is a very important concept is called face recognition, because that is because I used to teach AI and ML for my students, and I used to give the assignment on this speech recognition and this face recognition or some biometric system. In this way that suppose somebody would like to, there's an important concept, it's called the face spoofing. Okay, because if you would like to bypass your authentication by showing this your photograph, then how do you resist it? So this is called the liveness detection of a person. So now if you will have to write a good algorithm so that only this live person's things will be identified, not any photo. So this way that you can think of it as a face recognition. So biometric, you will have the different type of biometric system. You have physiological biometric, you have this behavioral biometric. Okay, sort of thing that you can have. There's another application you can have the data mining. There's a bioinformatics. All the fields are very, very interesting and important fields. So now what is your main task in classification? So you have to assign an unknown objects. So this object is called the pattern into correct class. Okay, you have a n number of class. Okay, you have a n class, or you can have C class. If class is denoted by W1, to you have this WC. You have C number of class. Now if you have going to have some unknown pattern, so if this pattern in the form of a x1 to xn, okay, if the pattern is can be determined x1 to xn, then this pattern is belong to either W1, okay, or W2, or it should be in WC. So now this is your job, okay, and this is called the classifications. Next, this is called the features. So as I already explained in the first lecture, that is called in the class, this is called the features. So the features are the measurable quantities. Sometimes these feature space and measurement space are used interchangeably. So you have to measure this quantity from the pattern. I mean, now these features will help you, I mean, to distinguish between these two entities. Okay, like how you can distinguish between these two entities. So you have to extract some kind of distinguishable attributes, which will help you in your classifications process. So this is called your features. Okay, and suppose if you have the features n observation, suppose if you have the n features x1, oh sorry, if you have n features like x1 to xn, then you can have, suppose you are going to have n features, because these are all are thus you can have the L features for this here, means you have this L dimension, and each one is the measurable quantity, means you could get its values. Measurable quantity means you can get its values. Okay, and you could form a vector. So this is called the feature vector, and this time it is known as a column vector. So this column vector will be denoted by here x1 to, you can write xn. Okay, so this is called the column vector. Now its dimension is L cross 1, means L row and 1 column. So now when you can write it, and this is this symbol is called a vector. Okay, and when I'll be writing x, then above underline, what does it mean? It is called the average, mean or average. I'll be discussing. But when I'll be using the x underline, then it is a vector. So vector means actually it is a point. So why the point is, x is a point in R. So it is called this R, means real line. Because we have two lines, one is called the real line and it's a complex line, or you can say the imaginary line. So now x is a point in R. So it is a real line which ranges minus infinity to plus infinity. Okay, so x is a point, but when I write is a underline, it is a vector. So when I'm going to as a vector, it has got n components. So if I write this n Rn, it means x will have this n component. So like x1, x2, x3, xn. So that is the meaning. So that means you can extract that many features, or when we used to say we have the n dimension features. What is the meaning of this? You have the n dimension, means you have a vector which has got the n dimension. So now these feature vectors are treated as a random vectors. Okay, so Next, you will have to design a classifier which consists of a set of functions whose values computed at x, and obviously you have trained the classifier by using some functions, and obviously this is a measurable quantity. Now you will have to test it. You have some unknown pattern. Now based on you have to make a decision whether this unknown pattern belongs to which class 1 or class 2. So now how the things can be done. So this is the process. Okay, first you have to acquire this pattern on the sensor, then you have to generate the features, then you have to feature selection, I have explained. Then by using the feature you have to design the classifier. Then after that there is a system evaluation. It means that the classifier that you have built based on your features, whether the classifier is working correctly or not, you will have to evaluate its performance. So there is a different I mean way of doing these things. So there is a performance evaluation matrix. So you have to use some accuracy, by using accuracy, by using precision, recall, F1 measure, ROC curve, okay, CNC curve. So all these sort of things by using, you can check that whether your classifier is working correctly or not. But whenever you're going to use some regression, then how do you, but for this to check this performance analysis of the regression, then you could use some error matrices. This means mean error, mean square error, root mean square error, mean absolute error. So these are the things. So you should remember that when you are going to use classification and when you are going to evaluate the performance of the classifier, so these are the matrices. It is not matrix, it is called the metric, 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 metric. Okay, sometimes it is, if you use some statistical metric, then also you can use it. Okay, so now there is a two type of, I mean mostly you have this supervised and unsupervised, but people are also working in the field on the semi-supervised and reinforcement learning. So in the supervised learning, this pattern whose class is known a priori, and for the unsupervised, this from the number of classes unknown, and no training patterns are available. So now I was explaining to you about the feature vector. So now mathematically how the vector can be represented. So now suppose A is a set. Okay. So and obviously this set is a finite set, and you have Rn and n-dimensional real space. Now how the n can be written? Rn, R into R into R. Okay. Now it is a real line, that it is a, actually it is a range is minus infinity to plus infinity. Then R square means it is in 2D. If you have R3, this is 3D, R4, 4D. Now when you could say the hyperplane, if the dimension is greater than 2, then you can say it is an hyperplane. I mean greater than 2, then it is called the hyperplane. Okay, so now this is a n-dimensional column vector. Now it is n cross 1. Okay, that this it is n cross 1. It is one vector. Suppose it is, if you are saying, so this vector is called the height of a person, and this vector is called the weight of a person. Then you are just going to, and you are going to take the how many people, n people. Okay, so that many persons height will be stored, and that many person weight will be stored. So then it is called the n-dimensional column vector. Now you would like to take the distances between them. Now one of the most things is called the this is called the disk D2. Okay, so that is called the D2 means Euclidean distance. So this is a square root of I is equal to 1 AI minus B square, and then you can say this is a D1. Okay, this is a distance metric. So it is called this Manhattan distance. So this is, we are just taking this absolute difference between these two quantities. Okay, so suppose if you just plot it in the Euclidean space, 2, 3 and 3, 2 are not equal. Okay, so next is that what I was explaining to you, that a function, when do you say the function is called a density function? If it satisfies two property. Suppose as this is x is a point, okay, in real line. Okay, actually x is a vector, and it is a column vector, and it has, so that now this is a px is a density function. So you can see that I have written in small p. Okay, so small p means it is a density function, and capital P means it is a prior probability. So now px, so x is belongs to Rn. Okay, is said to be a probability density function if it satisfies first property here. P, I mean this px is greater than is equal to 0. Okay, for all x is element of Rn, and another is called is that there is a area under the curve is 1. It means that you have a range, or you can simply write over here Rn. Okay, instead of when writing minus infinity to plus infinity, you can write is Rn. So this is a px dx. It means you can have px1 dx1, px2 dx2, px3 dx3 is equal to 1. If any function satisfying these two property, then you would say this function is called a probability density function. Okay, so now there is a another, there is a lot of density function. I mean this probability density function that it will follow some distribution. So why it is follow distribution? Because this px so will be returning some discrete values. Now if it is a discrete value, then obviously it is a probability values, and this density function will follow some distribution. Okay, now so there's called this triangular distribution. So now that is it is also a triangular density function. So a density function, this density function uh, following the triangular distribution, so that's why it is called the triangular density function. Okay, so I am assuming that all of you know the meaning of the distribution. Okay, that is called the probability distribution. When I'm telling the distribution, so it means this probability distribution. So now if it satisfies fx greater than is equal to, obviously, and area under the curve is 1. If you just calculate half base into height, so you'll get this one. So then you would say this is a, yes, I can take this is a triangular density function that I could take because it follows this the triangular distribution, and obviously it follows the property of this density function. Okay, so there are a lot of number of distributions are available. Okay, you could find in any book or any statistics book or any other book, lot of the distributions are available, and the data set that you will be working, so it is following different type of distribution. We have to check that which distribution that your data set is following. So suppose you have some data set, and you have checked that your data set is following the distribution number x. That does not mean that some other distribution y will not fit it with your data set. That you cannot say. Okay, so there is an important concept in the distribution that the statisticians or those who are doing some statistics course, so they are using this fitting a distribution. There is a call a fitting a distribution. So now we'll see that what is it. That's a similarly triangular distribution. We have the exponential distribution that you can say. Next, one of the most popular distribution is called the normal distribution. Okay, or you can say this is a Gaussian distribution. So now we are assuming that the data set that you are going to have, that whether it is following the normal distribution or not. So why we are always taking this distribution is following a normal distribution. Apart from the normal, we have some chi-square distribution, we have beta distribution, we have gamma distribution, we have binomial distribution. Okay, we have Cauchy distribution. There are a lot of distribution out there. If you follow the book, there is a called the linear statistical inference and its application. You will find there's a lot of how the distributions can be understood, and there's a fitting a distribution. Okay, there's a important techniques for the fitting a distribution is called, this is a very important. There's a called this chi-square fit, or this is called the chi-square test. That is there. Okay, suppose you are assuming that your data is following some distribution. Now if you just do some approximate text, or you have some exact test. Now if you see that your data is actually fitting a normal distribution, or actually the distribution that you are expected to fit, then it is called the actual fit. But there is another called, is called the approximate test. So approximate test means you are assuming that your data following a distribution X. Okay, then you are find these chi-square values, or you are just doing this chi-square fit. Okay, for this distribution. Now you are finding this, what is this, observed values of the chi-square test. Now you just note it down. Then if you check this observed value of the chi-square test after fitting a distribution, okay, is less than this your tabulated value of the chi-square. So for each distribution you can find some tabulated values. Then you would say that your distribution is following this normal distribution. Okay, so there is a way of understanding it. There is a called the fitting a distribution. Similarly, we are going to have a normal distribution. So now X is a random. X is called a random variable. Okay, now this random variable is sometimes known as, you can find the book is called the IID, the property IID. This is called independent and identically distributed random variable. So X, capital X, it is a random variable, but it is not right. It is the independent and identically distributed random variable. So what does it mean? Okay, suppose you have a coin. Okay, suppose you have a coin. Now you are tossing a coin and you are getting the head. You are getting head. Now in the second trial, so you have some another outcome. Okay. Now do you think that this first outcome, the first trial, will have any role to play on this second outcome on the second trial? It is not. It means that you do not. I mean, there is no impact occurred of the first trial on the second trial. Means that's why both the events are called the independent. Now identically distributed. Now you do not. Now in the first trial you are getting the head. Okay, these chances of getting head is 50%, and in the second trial the chances of getting head is also. I mean, these chances of getting tail is 50%. Now you do not want to change the distribution. You do not want to change the distribution of the data. If you just select the value and just put it back, then it is called the identically distributed. Okay, so that's why if any book or any research material, you can find that X is a independent and identically distributed random variable. So this is the meaning. So you are not going to change the distribution. So when you have get it, it is fixed. You do not want to change the distribution of the data. And it is, so that's why it is called the identical. And independent means both the event, this output of the first trial does not have any role to play on the output of the second trial. Okay, so that's why it is called this independent. So there is a normal distribution is there. So these are this univariate normal. That is a formula, is very common formula that you can use it. Next is called this, very important, is called the multivariate normal distribution. So now this multivariate normal, that is you can find that is a very long formula is there, 1 by root over 2 pi to the power a, determinant of sigma to the power half exp of minus half x minus mu transpose sigma inverse x minus mu. So this is very popular formula, and the base decisions rule that I'll tell you. So in practical example, that you have to implement the base decision rule and the density function which is given to you, that is called the multivariate Gaussian distribution, because it is a density function, probability density function, which follow this multivariate distribution. So now formula for it is this 1 by root over 2 pi to the power n, determinant of sigma to the power half exp of this expression. Okay, we'll see. So now these are the basics of statistics that all of you know, that how to calculate this mean of a random variable. So if you have this n observation, x1 to xn, and the mean of x can be computed. X is equal to 1 by n, I is equal to 1 to xi, that you can easily compute. And similarly, this variance you can just compute. So variance is just this, how much deviation is there from the mean. And why you are doing this square term? Because that is if any I mean negative term is there, and also these things can also be computed Okay, by the differentiation of this expression. Suppose if you see that how these things is coming. Suppose f of xi minus x bar. Suppose you have a function fa is equal to 1 to n is equal to 1 to n xi minus a whole square. Now if you just differentiate with respect to a f dash a and equate to 0 for at what values of a this function is that is minimized. Okay, then you can just check it. Then obviously you can find x. So why we are taking this square term? Because if you are going to have this negative term while differencing, then if you just square, then it will be cancelled. Now the concept of probability that you know if a is a random variable, and how do you calculate this expectation of x, that you can easily compute. So I'm just skipping it all these things because time is less. So these are the binomial distribution that you can, how do you compute this, what is the probability of getting hit for 3 times. Now this very important concept is called the covariance. So you know the concept of the variance. Now how do you know this concept of covariance? So I'll have to explain it. Suppose I have two variables x and y. So how do you find this covariance between two variables x and y? Suppose x is the height of a person, y is the weight of a person. Okay, now I have collected x for n people. Now I have this x1 to xn observation, so and it is denoted by xi, and I have this y, so it is denoted by x and y. So you are just simply plot it. Okay, you just simply plot it. Okay, now so after plotting these x and y, so I'll show you 3 different plots that you could see. Okay, so you may also have some other plot also. So it is called the two-dimensional space. So you can easily plot the x values, where x is their height. You can write it is an height, and y you can have it is an, you can say it is an weight w. Okay, you just simply plot this x and xi and y values. So now here you are going to see 3 different cases: case 1, case 2, and case 3. So just seeing these 3 plots are there. Okay, now in the first plots, these data points are like that. Okay, so you please concentrate only that part, not this another axis. So I'm just taking these data. I'm taking the observation. In observation means in people, and I'm just plotting. So this is my plot of this case 1. Now for the case 2, the plot is something like that. Case 3 for this. Now if you just look at the plot, and if you see the x-axis and y-axis, so x-axis is height, y-axis is weight. What you see, when the x values are increasing, the y values are more or less increasing. Okay. Now here on the case number 2, when the x values are increasing, these y values are more or less are decreasing. But on the case number 3, when the x values are increasing, these y values are on the same range. It means that I would like to denote the relationship, okay, with a quantity. So and this quantity is greater than 0. Now I would like to denote the relationship between x and 1. What type of relationship it will have? And I do not know that what is the quantity. So this quantity that I am denoting by r. So I would like to denote the relationship between x and y with a quantity. But this quantity is greater than 0 on seeing these values. Similarly, on case 2, I would like to denote the relationship between x and y. Okay, and this quantity is less than 0. And on the case number 3, I would like to denote the relationship between x and y, but this quantity is a more or less 0, because that for the when the x values is changes, so y value are in this on the same range, so that it is close to 0, that we can have. Okay, so now what I'll do, I'll just take the mean of these original data points. Now if you take the mean of the original data points, then I will have the mean is something like that. Now mean is denoted by x bar, y bar. Similarly, I'll take the mean for the other 2 cases. Now what I'll do, I'll just shift my axis from this to this. So this is my my axis, original axis was xy. Now my modified axis is x prime and this y prime. And this is my centroid point, I mean mean. Okay, now what I'll do, if you just check in the new axis on that, you have some data points in the first quadrant, you have some data point in the second quadrant, you have some data point you have data point first quadrant, second quadrant, third quadrant, and fourth quadrant. If you see the data point in the first quadrant, okay, now that if you see that suppose I'm taking these values. Now if you check these values, so this is my x values and this is my y values. Okay, similarly, if I check these things, so this is my x values and this is my y values. Okay, now if you just multiply them, then its values will also be large. It means that in this quadrant, okay, this x value is positive, y values is positive, and their multiplication is also positive, and also the value is also large. On the other hand, if you see in the third quadrant, this x value is negative. Okay, if you take any values, then y value is negative, but the product is positive, and the value is also large. Now you just check this in the first quadrant, you have more positive sample, third quadrant also you have some more positive sample. So it means that more positive samples are dominating the less negative sample. So that's why this relationship is called the positive relationship. Okay, similarly on the other hand, if you see in the case number 2, that is in the first quadrant, in this second quadrant, the x value is positive. This is called the negative positive. So now then their product is also negative. Okay, and here their product is also negative. Now here the places where this product is negative are large, then the places their product is positive. So that's why this is called the negative relationship. If you see the places where the product are negative, so they are large number, then the places where their product is positive. So that's why this is called the negative relationship. Similarly, but here, if you see all the things, so you have this, that all the points are equally distributed over this mean. So that's why you have this zero relationship. Now, if you would like to find what is the formula, then because what we are going to do, we are just going to product from the xi minus x bar, means what is the deviation, what is the deviation from original to original to new x coordinate, xi minus x bar into yi minus y bar. So it is an just multiply them and you have to do the average. So this is called this covariance. So now this formula, all of you see this formula already. The formula is 1 by n is equal to 1 by xi minus x by yi minus y bar, but it is coming from here. Now this correlation coefficient that you have, this is a rxy. So it is called this COB of xy divided by variance of x into variance y. It is just simply we are doing this angle between these two vectors. You just take the dot product between them, okay, and simply it is a cos theta. So now I'm just skipping all these things because I don't have time. So now next we'll have this probability estimation. So there is a estimation technique, so it is no need to recur. Okay, so I'll explain to you. This is a classification technique by using the base decision tool. Suppose I have some statistical nature of feature, that is x is equal to x1 to xl. I have the L dimensional features, and you have to assign the pattern represented by the feature vector x to the most probable. So the term is called, this is a most probable so far. So what does it mean in statistics? Okay, it means that out of these points, because you need to find this is a posterior probability that we used to find. So if you find any classical statistics book, so now this x point, so what is the belongingness of this x? What is the chances of x to classify in one of the classes? Now, which one will give it to the maximum probability? Then this x will be classified in one of the m classes. Okay, now you have to find what is the probability or what is the belongingness of x for this class. It means that it is something like that. What is the belongingness of x for this class? Suppose it is a W1. Okay, now W2. Okay, now you have the Wm. Now if you see that the belongingness for the class is called 0.2. Now next is called the 0.5. Now it is 0.9. Now obviously you will classify this x in the 0.9. So now that's why you have to assign the pattern represented by the feature vector x to the most probable, means which will give it to the maximum probability. What is the belongingness of a pattern to this class? Then you have to classify this is one of the n classes. So now that is denoted by x to wi. So that is, it is called the posterior probability, pwi x. Now what is the probability that x will belong to this class? Now which one will give it to this maximum? Then x will be classified as one of the classes. So now we have to calculate this posterior probability. Okay. Now what is the base rule that all of you know? What is the base formula? Now the base formula that all of you know already, this is very simple. This is called the posterior probability. So this is called the posterior, because it is coming from this base formula. Posterior is equal to, you have the likelihood, posterior likelihood multiplied by prior probability. So we have already seen capital P1, capital P2, capital PC. So it is called the prior probability divided by evidence. EVI. This should be I, evidence. So this is called the formula of the base theory. This is a posterior probability that you have to calculate probability of Wi given x is equal to. Now we'll see, you have to computation of a posterior probability and assume that a prior probabilities, that is I already told you, PW1, PW2, PWM. So now these things, this like capital P is always range from this capital P from this. If you have C classes, if you have, suppose here we are going to have M classes, then summation of is equal to 1 to M Pi is equal to 1. Okay. So now you have to calculate, this is called the likelihood function. So, and this likelihood function is nothing but a density function. This is called the probability density function that you have to estimate. But for applying the base decision rule, these things will be given to you. These things will also be given to you. Now, what is the decision rule that we will explain? So now this is called the likelihood function of x with respect to dot w1. Okay, so it is just nothing but a density function. So x, and this is a wi, means one class, w2 another class, then till if you have the, if you are going to solve the m class classifications problem, means wm. So total m number of class that you are having. So next, now what is the base rule? Now we will be seeing for the class for the m is equal to 2. So this is a fundamental approach. We will have to see m is equal to 2. Now you just put p of x, p wi x is equal to p of x, w p x w. So it is nothing but a, now if we simply have p of wi, this is called the posterior probability. So this is called the likelihood function. This is prior probability, and this is an evidence. And this evidence that we are ignoring this denominator part. Why? Because this is same for all the classes, I mean both the classes. So that's why this denominator part we are eliminating, because only because of these things there. So it is just as you can see the scalar factor, and this is a same for both the classes. Okay. Now now what is the base classifications rule? Now for the two class classifications problem, now given x, classify it according to this rule. Now the rule is that if capital P1 for the two class, capital P1, small p1 x x is a test vector. Okay, if capital P1 once P1 is greater than is equal to capital P2 small p2 x. Okay, then you would say that you have to calculate this density function for the first class and the density function for the second class, then you just multiply them. So this is nothing but a prior probability. I mean this it is a posterior probability. So simply this p, if p w1x is a posterior probability is greater than p w2x, then x is classified to w1. So now when I am going to have the equality sign, it means that you can, when you find these two values are equal, then you can place x in one of the two classes. That does not matter. Okay. Now if pw2x is greater than these things, then x is in w. Now equivalently, so this can also be written in this way, that as I have already written here, that is a p of w1, that is a p1 simply, and px w1, so that is a p1x. Okay, as I am not writing 1 over here, it means it is a class 1, and p2 means this is in class 2. On the other way, you can also write px w1 or px w2. So for the equiprobable classes, so when you are going to have the equiprobable class, means when the prior probability are equal, means p1 is equal to p2 is equal to half. So this is called the equiprobable classes. Then only you can have pxw1 or pxw. So this is for, this is a class 2. So now simply in order to understand it, because whenever you are doing some classifications now, so you will have some classifications error. So you will have some misclassifications. Whenever you are going this classification, you will have some misclassification. So now in order to understand it, suppose I am going to plot the density function, or here I am going to consider only one features. So out of my x is my is RL. Okay, now my L is 1 here. So my L is here 1. L is, my dimension is 1, means only 1x. So that's why I have only 1x. Okay, now this is my feature, that, and this is my, that is a feature space. I mean the way you are going to plotting the density function. Now here pxw, so this is a density. Now I am assuming that I have my density function is a Gaussian. Now for the first class, my density curve is like that, pxw1 for the first class. Now for my class 2, my density curve is px means w2. So there is some overlapping region. Can you just see? So this is the overlapping region. Okay, so this shaded area is called, this is a misclassifications are occurred in this area. Okay, and if you just take the intersection point, and this intersections point, if you just paint it in x0, then you can divide these two space. One is called the R1 space, another is called the R2 space. Now you can say that actually here this confusion matrix can be done. How? Because actually the point R actually belong to W1, but it classified to R1 region. So now next is, if a point is actually from W2 but is classified to R2, then it is an error. So now here we will be considering this, what is this probability of misclassification error. So this, whenever you are going to do classification, you have to do some probability of misclassification, and this is called this confusion matrix. So here you can have this actual, you can have, and here you will have to some decision rule. Okay, then you can have point actually from class 1, it are point classified in class 1, classified in class 2. Okay, and point actually from class 1 and point actually from class 2. Okay, now if a point is actually from class 1 and classified in class 1, then there is no problem. But the point is actually from class 1 but it classified in class 2, then there is an error. Similarly, when a point actually from class C2, but it classified in class C1. So there is an error. Now this point is actually from class C2 in classified in C2. There is no problem. So similarly here you can see, so these are this area where this misclassification happened. You would say that point is actually from class 1, but it classified to R1. So this, so there is an this region. So now there is an error. Similarly, this point actually from W2 and it is classified to R2. So this is an error. Now you have to calculate this. What is this probability of misclassification error? Here we are not going to consider this. What is the cost of misclassification? The cost of misclassification is different than the probability of misclassification. So please understand. Okay, so when I will be considering, it may so happen that the cost of misclassification is less, but the probability of misclassification may be high, or in the vice versa. But when I will be discussing this cost probability of misclassification, then I am assuming that, so I am going to give this equal weight to this error. I am going to give the equal weights for the error, but it is sometimes not good. Why? Because suppose somebody would like to do some doctor would like to do some diagnostic passes. Suppose if you would like to do classification whether this tumor is a malignant tumor or it is a non-malignant tumor, the benign tumor, and if you would like to give the same weightage for both the error, then you will have a problem, isn't it? You will have some problem. So suppose actually if the person does not have a malignant tumor, okay, but it is wrongly classified is a tumor, okay, there is no problem, but in some clinical trial you can detect. But if the person is actually having a tumor, but it is detecting that it is a non-tumor cell, then there is a problem. So that's why all the time, if you would like to put the equal weights to the error, so it is not okay all the time, but you have to see what this problem under consideration. Okay. So similarly, that this space that I explained to you, so you can divide into two regions. So now, if the point X is the element of R1, then you can put X in this W1. Now, if it is an R2, then you can put in this data. Now, what is the probability of error? Then you have to calculate the total shaded area. Now, this PE will be now minus infinity to H naught, because as we are having some range where I can distinguish between R1 and R2. Okay. So from this infinity to X naught, I have R1 space. From X naught to X, so I can have this R2 space. Okay. So it is for a general way of representation, but when we have solving some example, the range will be given to you, or you have to calculate. Okay. Now P will be, so what does it mean? So you can write here what I should write. It is, I can write here R1. So I can write here R1. Okay, or I can write here R2. So what does it mean? That the point is actually from W2, but it is classified in R1. So now you have to calculate this error. You have to do the integration. Okay, and this point actually from W1, but it is classified in W2. So it is an error. So now P is the total error that you have to compute. Now base classifier is said to be an optimal classification technique because it minimizes this probability of misclassification error. So Bayesian classifier is an optimal classifier. So please remember, it is an optimal classifier. Why it is an equal to the optimal classifier? Because it has got a solid mathematics background to prove that it minimizes the probability of misclassification error. Okay. So now if you just change the, if you just move the threshold, so these are the threshold. Okay. Like you are just increasing the threshold in the left hand side, then you are just dominating this axis R1 space. Okay, and you are not this R1 is increases, then R2 is decreases. But similarly, if you just move this axis in this direction, then R1 is decreases, R2 is increases. So this way that you can just think of it. So now Here we'll see that base classifications for this. If you have this class is greater than 2, then how these things can be classified? Then PWIX is greater than PWX. Means I can write this formula instead of writing 2-class classification problem. I will have this M-class classification formula. It means capital PI. I should write this formula will be for M-class classifications problem. I have to write capital PI, small pi, x is greater than equal to capital PJ, small pjx, for all j is not is equal to x. Okay, so it is just a posterior probability. Okay, it's greater than this thing, and it also minimizes this classification error probability. So now, so here we are not considering the cost of the misclassification. Now, if you consider the cost of the misclassifications, then you will have to minimize the risk, or because as I already taken the example of the medical diagnostic system, and where this, so every time this you cannot give for the equal error rates, so you will have to have some penalty term that has to be incorporated. So now whenever you are going to take a wrong decision, now this penalty term has to be assigned. So now how the penalty term can be assigned when you are going to take more sensitive decision than other. Then when you are going to incorporate the risk, then you have to find what is the average risk, and you have to minimize this average risk. So although you are going to incurring some cost for taking a wrong decision, but you will have to minimize this cost. So how to do this? Suppose whenever you are going to doing these things, then for the 2-class you have a loss matrix. Suppose 2-class classifications. If you see this, I was explaining to you the confusion matrix. Now, if it is a correct classification, means this is a cost is there is a no cost. I mean this is correctly classified. So L11 and lambda 11 and lambda 22 means that it will be cost is 0. Okay, because it was correctly classified. But lambda 12 and lambda 21, these are this cost, because for taking a wrong decisions you have to incur some loss. So this is a L, and for the loss for means what does it means? Lambda 12. So pattern actually belong to class 1, but it is wrongly classified to class 2. Then this what cost it is incurred? Lambda 12. Similarly, lambda 21 pattern actually from class 2, but it is classified to class 1. Then this cost. Now this 1-2 penalty term for deciding class W2, although the pattern is belongs to W2, already explained. Now you have to minimize the risk. Now how the risk can be defined? So R1 risk with respect to W1. Then you'll have to simply write a lambda 1 so for this matrix. So you can already write. I mean it is correctly classified, so there is no problem. But for these things, this is a rectangular box, so this is an error. Or this cost is this thing, say lambda 12, and this term has already there. This is a density function that you know already, and there is a risk with respect to W2 for the other class. So this is this cost that is for wrongly classified, but is correctly classified. Now this rectangular box or this expression, it is a wrong. This penalty is incorporated, which is for taking a wrong decision. So now how we are going to you need to do the average risk. The R is equal to R1 PW1, so capital PW1 means posterior probability, and R2 into capital PW2. Now you have to choose R1 and R2. I mean you have already seen the region. Okay, one is called this entire space. Entire feature space has been divided into R1 space and R2 space. Now you have to choose R1 and R2 in such a way that R is minimized. As I was explaining to you this, we are taking this one threshold value x0. Now you have to choose the x0 in such a way. Okay, either you can move the x0 in the left directions, or either you can move the x in the right direction based on that. I mean, which things are you are going to compromise. Then this R1 has to be minimized. Now you have to assign x in Wi if this L1, this risk is equivalent to this expression. So L11 Px, I'm just expanding. Okay, you can write x to W1 if this expression, the whole expression that I was written, is less than of this expression. Okay, equivalently you can say I can assign x either in W1 or W2 if I would have L12. L12 is called my likelihood ratio, means pattern is actually from class 1 but it is classified to class 2. Then you have a likelihood ratio, means what is the ratio? This is called the likelihood function. I already told you, because from the base rule, so it was actually a likelihood into prior by evidence. So now this prior probability we are having this equal. Okay, so now I am going to have pxw1 pxw2 which is greater than or less than. If you are going to classify x into w2, then it will be less than. If it is w1, then it is a greater than. There is a pw2 by w1. So here we are going to subtract. So these two expressions are, we are going to subtract in this way, or you are going to rearranging it so that you could get lambda 21 minus lambda 22 by lambda 12 minus lambda 11. So we are just going to do in this way. Next, if you are going to have that our prior probability is equal, and as I already told you, so this lambda 1 this cost is 0, lambda 1 is equal to lambda 2. I mean penalty is 0 because both this, because 1 means pattern is actually from class 1 and classified in class 1. So obviously, so it is a correct classification. Then you can put x in W1 if pxw1 is greater than pxw2. Okay, so it is a density functions, and this is your scale. So this scale factor, obviously it is less than 1. Okay, if you find it, and this, whenever you are going to do it in this way, so this cost of misclassification is close to the probability of misclassifications. Similarly, for x is belong to W2, if this entire pxw2, because why I am going to write capital P, because ultimately when you are going to have the density function, then you will have the discrete value. Now discrete probability values. So to identify the discrete probability values, we are going to have this capital P. Now this capital pxw2 is greater than of pxw1. Okay, then this lambda 12 by lambda 21. So if based on under consideration that that how we are going to select the region, if you are going to compromise this R1 region, okay, then your R2 region will be the point will be classified in the R2, and if you would like to compromise R2, then your point will be classified in R1. Because when one region is in, if you just move the threshold in forward and backward, then one region is increases and another region is decreases. So there is this is just simply a for the decreasing and increasing region of R1 and R2, this point will be classified accordingly. That's it. Okay, and this lambda 21 and lambda 22, so this is called the minimum classification error probability that you can calculate. So this is called a very good any book that you can find it, but you have to understand the confusion matrix first, and then only everything will be clear. So now my last part that I'll just quickly complete because I am having only 20 minutes to complete. This is how a person can implement the base decision rule on the satellite images. I'll just quickly go through it. So suppose this is the example of the satellite images of Kolkata. Actually, this image is taken from this ISI Kolkata. So I implemented it during my time, PhD time. And this is a urban images that you can find for each image size is, so so this is a Hooghly river. So this is a Hooghly river. So it is called the river region, and this is called this non-river region, means land covered area. So now you have to apply the base decision rule to identify which region is a river region and which region is a land covered region by applying the base decision rule. And you have 4 images, means 4 dimension data is given to you. One is R band, red band, G band. This is an input which will be given to you. B band, and you have the I band images. So 4 images that will be given to you. and after applying the base decision rule, you will get this output. So you have to have the river class, which will be denoted by white. I mean, you will have the 0 to 255. When it is 0, it is completely dark. When it is 1, I mean, or 255, then you will have this white. Okay, and you have the base rule. Then, as I already told you, the density function will be given to you, and this prior probability. So prior probability for the first class is 0.3. Prior probability for the second class is 0.7. Obviously, misclassification error rates are there because this is a dot pixel which must be classified in that region, but it is wrongly classified in this region. But you have to minimize this probability misclassification. So for the 3 different sets of prior probabilities, so you can have these 3 different output images. So now how do you implement it? So now four satellite images. So it is called this the feature vector dimension is 4, and each pixel locations we have 4 different values. Okay, means actually image is, so what do you mean by image? Image is nothing but a matrix xy. So it will have that is a, you have a matrix, you have a xy positions. Okay, so it is called your x-axis, x value, and this is your y. Okay, so this is your matrix value. Okay, and this feature vector dimension is 4, and each pixel location you have 4 values. So you have 2 classes. One is called the revert class, another is called, you are having this non-revert class that you are having. Now you have to choose the 50 sample points because you have to choose this 50 training samples point. Now how do you choose this 50 samples points? Suppose this is your area. Okay, so now you have to just choose 50 sample points, means 50 coordinate position, xy coordinate position that you could choose. So now from this paint, you just go to this IMSO function is there in MATLAB. Then you just just put the cursor in the particular place. Then you can have this 50 sample point. So now you'll have to choose the sample points in such a way so that entire region of the in the river class will be covered, because they should not choose 50 sample points only one part of the river region. If you just do it, then you'll have a lot of misclassification error. Why? Because when you calculate this mean, if you calculate this mean for over the entire region of the river area, your mean will be something like that. But if you are going to choose 50 sample points only that many area, so your mean will be something like that. So it will deviate from your actual mean. Okay, so please remember, whenever you are going to choose the data points randomly, that you should choose from the entire region, because this because your mean will represent this this is an overall variability of the class. So mean will represent the overall variability of the class. So similarly, for you have to take 100 sample points. This is called the pixel coordinate position from this non-river class. Now you have to take the entire samples 512 into 512. Okay, you have to just make a loop from I is equal to 1 to 512, j is equal to 1 to 512 for testing each band. Now you have to apply the base decision rule to classify whether the test samples will belong to either 0 or 255. Okay, now show the result in the black and white images. Now how do you choose it? Choose the sample points. As I already told you, IMShow function is there. Then you can use IM tool, or you can use some is a Python programming language. Okay. Then also you can just put this cursor in a particular place. You can get it. So here, for your sake of understanding, so I have taken x coordinate river, y coordinate river. So it is xy positions, not the intensity values. It is just a positions. I am having this 512 into 512 image. So I'm just taking this position. Huh? So next, this is the base decision rule. You have the M class. You have a class condition and density function, that is P1x, P2x, Pmx, where x is an element of Rn. Now this prior probability will be given to you. as I already explained. I is equal to 1 to m, pi is equal to 1. Put x in class I if uh, capital Pi, small pi x greater than capital P small p x, then it minimizes this base probability of misclassification. That's what is base decision rule. Now, how to implement? You have to implement process by first you have to calculate the density function. So now here the density is called this multivariate Gaussian. So you know this what is the formula. In order to apply this formula, I need to do in a subpart so that it will be this we'll have the quick computation. Now you have to calculate this mean of the river class. So your mean will be T1 for the river class. This is mean 1, mean 2, mean 3, mean 4. So their mean is this. You have 4 mean because as you are having the 4 different images. So mean 1 for R-band image, mean 2 for G, mean 3 for B, mean 4 for I. So total 4. So now this is your you have the mean will be 4 cross 1. So you have a mean vector. So now this mean vector will be 4 cross 1. Okay. Okay. So now actually your data set is a feature vector dimension is for the class for this first class means is a river class is 50 cross 4. So feature vector dimension for the class 1 is 50 cross 4. Now you have to take the column wise mean. So first column river class A, R band, G band, B band, I band. Then you have 4 cross 1. Similarly, for class 2, for this non-river class, you have 100 sample points, you have this 4 mean. Now you have to calculate this covariance matrix. Okay. Now we have already seen what is a covariance. Now if you have a covariance matrix, so now if you have n cross n feature, then this covariance matrix dimension will be n cross n. Now if you have, we are having this how many features? 4 feature. Now total covariance matrix dimension will be 4 cross 4. Okay. So now how it is coming? COV of 1, 1. You have to calculate covariance of red band image into red band image, then COV of red band image into green band image. Okay, so you can fill it in this way. COV of 1, 1. You can write COV of 1, 1 means first image into first image. First image with first image it is a variance. Then you have to calculate COV of second image with first image 2, 1. Okay, then COV of you can have 4, 1. I mean 3, 1, 4, 1. Similarly, you have to fill it up. So to total 4 cross 4, I mean total 16 elements that you will get. So they are going to get this covariance matrix. Now you have to calculate covariance matrix for this non-river class. Okay, similarly you will have this 4 cross 4. Now you have to test it. For testing, you have to take the entire image. Now entire image is called the test data set. Okay, now you have to run the loop from I is equal to 1 to j is equal to I is equal to 1 to 4 1 to j is equal to 1 to 4 1. Now the dimension of the test data is 4 into 512 into 512. Now you have to take each and every pixel and you have to calculate the density function. Okay. Now you take each pixel and you have to make a loop from I is equal to 1 to 512 to j is equal to 1 to 512. Now you have to calculate the river class, the density function. Now you know this formula of the density function in the x is 1 by root over 2 pi to the power n determinant of sigma to the power half exp of minus half x minus mu transpose sigma inverse x minus mu. Now these things that I am just computing here. Okay, for the river class. Okay, it is that part within this exp that I have already computed. Now you have to calculate the density function P1 for this class, and my capital P1 is 0.3. Now this is a 1 by, you just see that is a density function P1 means first class 1 by root over 2 pi to the power n. So it is constant for both the class. It will be cancelled out. Now then I have the another term. This is the determinant of sigma. So sigma is a covariance matrix. Now you have to take the determinant of sigma to the power half means square root. Okay, into exp of half means 0.5 into river class. So for the river class I have already computed. This is a x minus mu transpose. Then this covariance matrix sigma inverse. Okay, the sigma inverse then x minus mu. So this is this formula. Then I already computed for this non-river class. We have to compute it. Now for each pixel location you have to use this base decision rule. What is the base decision rule? Capital P1 small p1 is greater than is equal to capital P2 small p2. Now you check output image I comma j, because this image that you need to display, so that is also uh, is your black and white images, or I mean grayscale images. Now output image I comma j, obviously it is from 512 to 512 you will have. Okay, so either 255 or you will have this 0. Now you go to step number 7 again for each and every pixel location, and you will have to show this output for the 3 different classes. Then you will have this 40 different output. So that is the implementation perspective that you can apply. This is one of the most popular base decision rule, and if you would like to develop your own classifier and you would like to check that you would say that whether the classifier is said to be optimal classifier or not, then you'll have to check the misclassification error. Now, if the misclassification error of, or you can say the probability of misclassification error of your your design classifier is close to the base decision, this misclassification error of the base decision rule, then you would say so your classifier is an optimal classifier. Okay, so that is the things. Okay, thank you so much for your kind attentions. So if you have any questions,
Thank you so much, sir, for your wonderful session. I request all the
thank
faculty
you, madam.
members or participants to please give your feedback and the quiz so that we can score accordingly. And the link will be active for 15 minutes more. So please give your feedback and uh, quiz. Thank you so much, sir. Any of the participants, if you are having any doubt, you can ask. Mr. Peter, you want to ask any question? Please, sir is waiting. If anyone is having any query, you can ask. Okay, so I think uh, we should end our session.
Okay, madam,
Thank
thank
you
you
so
so
much,
much.
sir.
Thank you so much for inviting me for this session.
Thank you, sir. Thank you, all the participants. We will meet tomorrow morning, sharp 10 a.m. for our second day session and session number 3. Thank you so much. You can left the meeting.